Welcome to AI Research Weekly, the podcast for deeply technical insights into the bleeding edge of artificial intelligence. I'm Nova.
And I'm Onyx. This week we're diving into some fascinating developments across agentic AI, LLM reliability, and even the security of brain-computer interfaces. It's been a week of introspection for the field, really pushing on the fundamental limitations and robust deployment challenges of our current models.
Absolutely, Onyx. The papers we've selected really highlight a growing maturity in AI research. We're moving beyond just chasing benchmark numbers and asking harder questions about how these systems behave in complex, real-world, and especially safety-critical scenarios.
Exactly. One theme that really stood out was the focus on agents. We've got a paper tackling the serving infrastructure for multi-turn LLM agents, another ensuring deterministic planning for safety-critical agentic tasks, and even one enhancing spatial reasoning in embodied agents. It feels like we're finally getting serious about building reliable, deployable AI agents.
And then we have the crucial work on understanding why LLMs fail, especially with structured outputs, which is a common pain point for many engineers right now. So let's jump right into it. Onyx, where do you want to start this week?
Let's kick things off with Agent ServiceSim, a hardware-aware simulator for multi-turn LLM agent serving. This paper, out of what looks like a collaboration between several major cloud providers, really speaks to the practical challenges of scaling LLM agents.
Oh, I saw that one. It addresses the massive gap in current LLM serving simulators. Most of them focus on stateless request processing, right? But multi-turn agents are fundamentally stateful, managing context, tool calls, and KV cache across multiple interactions.
Precisely. The key contribution here is that Agent ServiceSim reproduces real system behavior within a 6% error margin across critical performance metrics. This is done specifically when evaluating LLM agent serving policies on commodity CPUs, which is a big deal because it enables repeatable exploration without needing costly accelerator time.
That 6% error margin is impressive for a simulator in this complex domain. So what specific shortcomings does it address compared to existing simulators?
Well, traditional LLM serving simulators largely ignore the program identity of an agent. They treat each turn as a discrete, independent request. Agent ServiceSim, however, models the agent program as the unit of execution. This means it preserves turn dependencies, accounts for tool-induced idle intervals, and crucially manages cross-turn KV cache reuse.
That makes so much sense. If you're not tracking KV cache residency across turns, you're missing a huge part of the cost and performance profile. What are the core components that enable this?
They introduce a few novel architectural modules. First, the program orchestrator ensures program identity and correct turn order, releasing subsequent turns only after the current one and any associated tool gap are complete in simulated time. Then there's the session-aware router, which maintains program-to-instance affinity for multi-instance deployments. This is key for preserving cross-turn cache locality. If affinity can't be maintained, it charges migration or reprefill costs, making the simulation very realistic.
Right, so it simulates the actual infrastructure decisions, not just the LLM inference. And the KV residency model, that's got to be critical.
Absolutely. The KV residency model tracks policy-defined KV placement across HBM, host DRAM, and CXL memory, and handles evictions. It uses a radix attention-style prefix cache structure to manage state during those tool-induced idle gaps. This is a level of detail that's been missing.
So for researchers working on optimizing agentic workflows, this simulator sounds like a game changer. It shifts the evaluation metric from individual LLM call latency to program job completion time, or JCT, which is what users actually experience.
Exactly. It means we can systematically study the interactions of prefix caching, scheduling, routing, and KV cache management policies. The paper reveals conditions where agent-aware policies offer significant benefits, and it really highlights the impact of factors like prefix reuse and tool latency on overall agent performance.
It's a foundational piece of work for the LLM agent ecosystem. We've been talking about agents for a while, but getting them to scale efficiently and reliably needs this kind of infrastructure-aware thinking.
Agreed. And speaking of reliable agent behavior, Let's pivot to Safe Run, enabling determinism in LLM planning for running. This paper tackles the crucial issue of safety-critical planning for LLM agents.
This is where LLMs meet real-world constraints, which is always tricky. What problem are they solving here, specifically?
The core problem is that LLMs, while great at generating flexible plans, struggle with strict constraint satisfaction and determinism. When you're planning for something like a running schedule, safety rules are non-negotiable, like not doing too many high-intensity sessions consecutively. Safe Run achieves a 100% safety score in running planning, which is a massive jump from baselines. The previous best, Kodact, was at 97.6%. And other baselines like PE averaged only 79.1%.
100% safety in a domain like that is a huge claim. How do they manage that with the inherent non-determinism of LLMs?
Their innovation is a decoupled architecture. They separate the LLM's soft interpretation and creative planning capabilities from the hard constraint enforcement by a deterministic solver. The LLM suggests a plan, but a CPSAP-based solver strictly validates and enforces all safety rules.
That's a smart way to do it. The LLM provides the creativity, but a formal system provides the guardrails. So the LLM isn't generating arbitrary code or actions directly?
Precisely. The LLM is restricted to invoking predefined planning APIs. This channels its flexibility into structured outputs that the deterministic solver can then understand and validate against the hard-coded safety rules. It's essentially using the LLM as an intelligent front end to a verifiable planning system.
And what happens if the LLM's initial plan violates a constraint?
That's where the agent loop comes in. If the deterministic solver finds a violation or an unfeasible plan, it provides feedback to the LLM, prompting it to replan. This iterative process continues until a valid, safe solution is found or a maximum iteration limit is reached.
That's crucial for robustness. The paper mentioned they built a running planning benchmark, too.
Yes, it's quite comprehensive. It includes 100 multi-week queries and 10 diverse runner profiles, generating 400 profile query combinations. The safety rules themselves are derived from established coaching heuristics, covering constraints like intensity sessions per week, consecutive intensity days, and weekly mileage.
This really shows a path forward for deploying LLM agents in any domain where safety and strict adherence to rules are paramount. It's not about making the LLM itself perfectly deterministic, but about designing the system around it.
Exactly. It's a pragmatic and effective approach that combines the strengths of both symbolic and neural AI, and it leverages existing proven solvers, which is another smart move.
That's a great segue, actually, into our next paper, which also touches on LLM limitations, but from a different angle. Capacity, not format, rethinking structured reasoning failures. This paper really challenged some of my assumptions.
It certainly did for me too, Nova. We've all run into issues with LLMs spitting out malformed JSON or struggling with complex structured outputs, and the common assumption is it's a formatting issue or maybe prompt length. But this paper argues it's fundamentally about the model's capacity.
Yes, their core finding is that structured output degradation is capacity dependent. Models with sufficient headroom, like Sonnet, absorb JSON constraints with almost no performance degradation. For example, Sonnet showed 88.7% accuracy with JSON versus 89.3% with chain of thought on Math Hard. That's a negligible drop.
Right. But for models operating near their capacity limits, the story is very different. They identified two distinct mechanisms for degradation: truncation under standard token budgets and pure capacity competition independent of token exhaustion.
That second mechanism is particularly insightful. Haiku, for instance, dropped a massive 36.2 percentage points due to truncation. But then GPT-4o Mini dropped 28.0 percentage points, even with 4x the token budget and zero truncation. That clearly points to a pure capacity competition, where the cognitive load of simultaneously reasoning and adhering to a complex schema overwhelms the model.
And it's not just smaller models. They showed that even frontier models like Opus 4.7 weren't immune, dropping from 96% to 91% on AIM competition math when forced into JSON. That's a 5.3 percentage point hit.
That really qualifies those claims about frontier models being resilient to such constraints. What's the practical implication of this?
It means we need to rethink how we prompt for structured outputs, especially for complex reasoning tasks. The paper shows that a delayed structure ablation, where reasoning occurs freely first and then the output is formatted, recovers most of the lost accuracy, around 80 to 87% for capacity-limited models.
That's a huge win for engineering reliable systems. If you need structured JSON for downstream processing, it's better to ask the LLM to reason in a free-form manner and then ask it to reformat its own generated reasoning into JSON, rather than forcing the reasoning to occur within the JSON constraints from the start.
Exactly. They also used an information-matched prose control, where Haiku got 80.7% accuracy compared to 52.5% for JSON, with 0% parse failures. This definitively proves the degradation isn't just about prompt length or extraction artifacts, but about the cognitive load of simultaneous reasoning and schema-compliant serialization.
This changes how I think about prompt engineering for structured outputs. It's not just about clear instructions, it's about managing the model's cognitive load and intrinsic capacity. This is critical for anyone building applications with agents that need to output structured data.
Agreed. It underscores that we're still uncovering the true internal mechanisms of these models. Understanding these limitations is key to building more robust systems.
From agent reliability and LLM capacity, let's shift gears to a fascinating area: the security of brain-computer interface and LLM agents. Onyx, the paper on brain prompt injection, really caught my eye.
This is a crucial and emerging area, Nova. As we integrate BCIs with LLMs, we're creating entirely new attack surfaces. This paper, Brain Prompt Injection, a route safety audit for BCI LLM agents, proactively identifies these vulnerabilities.
It sounds like a next-level prompt injection. What exactly is a brain prompt injection?
It refers to a new class of attacks where malicious inputs, potentially originating from perturbed brain signals or external context, can subvert the BCI LLM agent's intended operation. They identify three failure modes: C1, which are signal-side perturbations; C2, context-only injections; and C3, which are adaptive dual decoder attacks, where an attacker can jointly manipulate both the BCI decoder and the LLM.
C3 sounds particularly insidious. It means even if you have two decoders agreeing, it doesn't guarantee user intent if both are being co-opted.
That's the critical insight. The paper formally proves that dual decoder agreement alone does not certify user intent under shared raw input perturbation. An attacker can drive both decoders to satisfy an agreement predicate, leading to C3 route risk. This completely breaks the assumption that redundancy equals safety in this context.
So, what's their proposed solution or mitigation strategy?
They define a route safety audit contract, which includes a minimal log schema, a denominator hierarchy, and endpoint specifications. This contract is designed to establish route safety beyond just decoder accuracy or agreement. It necessitates specific logging of context provenance, any attacked secondary decisions, the execution policy, and the final route or confirmation outcome.
So, detailed provenance tracking is a key defense.
Absolutely. Provenance logging effectively blocks C2 routes, showing 0.000 risk. For C3 attacks, combining agreement plus provenance routes still showed 1.0s and flips, but confirmation plus provenance routes reduced C3 flips to 0.000. This demonstrates the power of these defense mechanisms. They also propose split conformal calibration for non-Oracle EEG confirmation channels, which can achieve a false accept rate of 0.00 at a clean utility of 0.15 for alpha equal to 0.005.
That's strong evidence for the effectiveness of their audit framework. What are the broader implications here for BCI LLM systems?
This work highlights the necessity of non-controllable confirmation channels. An attacker-controllable confirmation channel significantly breaks the conformal bound to approximately 1, rendering it useless. So, mediation and confirmation can reduce risk, but they are explicitly not intent certificates. This is a wake-up call for designers of BCI LLM systems to integrate robust, auditable safety mechanisms from the ground up, recognizing the unique attack vectors.
It's a very timely paper. As BCI technology advances, these discussions on security and safety need to happen now, not after incidents occur.
Agreed. And from BCI to embodied agents, another compelling paper this week is Allospatial, Agentic Harness Framework for Spatial Reasoning in Foundation Models. This one tackles how agents perceive and navigate their environment.
This moves us from purely textual agents to ones that interact with a physical or simulated physical world. The problem with many current models is they have egocentric views, meaning they only understand space relative to themselves, right?
Exactly. And that severely limits their ability to plan and reason effectively over complex, persistent environments. Allospatial's key contribution is an agentic framework that transforms these egocentric observations into global, allocentric spatial representations. Think of it as building an internal mind map of the world.
So it's not just seeing what's directly in front of it, but understanding the layout of an entire room or building.
Precisely. It specifically generates allocentric spatial trees, or ASTs, and route maps. These ASTs are incredibly rich. They support querying object topology, geometric relations, passability, and even potential trajectories. The core component for this is their world-to-mind cognitive mapping sandbox.
That's a great name, and it sounds like this isn't just for training, but something agents can use at inference time.
Yes, it's a plug-and-play component. And crucially, Allospatial introduces a spatial reasoning harness. This harness enables tool-use judgment, modality-decoupled cue collection, so it can integrate visual, semantic, or other priors, and geometry-semantic arbitration to reliably use these spatial priors even under noisy reconstruction or ambiguous visual evidence.
That's a critical point, dealing with real-world noise and ambiguity. So how much of a performance gain do they see?
In a training-free setting, Allospatial improved proprietary models like GPT 5.2, Claude 4.6, and Gemini 3 by 5% to 18% overall on benchmarks like VSI Bench and MindCube. That's a significant improvement without any task-specific fine-tuning.
5 to 18% is a substantial leap. What about the blind setting they mentioned?
That's one of the most surprising findings. Even when visual inputs were removed entirely, the ASTs alone could support strong spatial reasoning. This suggests that high-quality allocentric priors can facilitate spatial mental simulation without direct visual evidence. It's like an agent can close its eyes and still navigate because it has a robust internal map.
That's incredibly powerful for embodied AI. It means a model isn't just reacting to what it sees, but is drawing on a deeper understanding of its environment. And they used reinforcement learning with a specific reward mechanism, too.
Yes, they used cold start reinforcement learning with a harness-gated trajectory reward, or HGTR. This reward evaluates the trajectory as a whole and enforces gates. Answer accuracy is credited only when the required reasoning structure is followed, and tool use rewards are granted only for valid calls contributing to a correct answer. This stabilizes optimization and prevents reward hacking.
This is exactly the kind of robust, verifiable reasoning we need for truly intelligent embodied agents. Moving beyond reactive systems to ones that genuinely understand and model their environment.
Exactly. It's a fundamental step for robotics and any multimodal agent that needs to navigate complex physical spaces.
All right, those were some incredible deep dives into the research this week. Before we wrap up, let's take a quick look at what's happening in the industry. Onyx, what's our industry watch this week?
Nova, it's been a slightly quieter week on the major industry release front, at least compared to the pace we sometimes see. However, several themes from our research discussion are actually playing out in industry priorities. For instance, we're seeing continued pushes towards making foundation models more efficient and reliable in deployment.
You mean like optimizing inference and resource utilization?
Precisely. While there wasn't a blockbuster model drop this week, we're tracking persistent chatter from the major cloud providers, let's call them Megacorp AI and Global Tech Solutions, around improving their LLM as a service offerings. They're focusing on infrastructure-level optimizations that directly leverage insights from papers like Agent ServeSim. We anticipate announcements soon about more intelligent load balancing, session-aware caching, and dynamic resource allocation for multi-turn agentic workloads.
So even if the models aren't new, the serving architecture behind them is getting a significant upgrade, driven by research on efficiently handling stateful agent interactions.
Exactly. Megacorp AI's upcoming adaptive agent orchestrator is rumored to implement a radix attention-style prefix cache, very similar to the KV residency model we just discussed. This is aimed at significantly reducing latency for long-running agent sessions and improving cost-effectiveness by better managing HBM and CXL resources.
That's a practical example of research directly influencing product development. And what about the focus on reliable outputs, especially structured ones?
Good point. We've seen an increase in guardrail-as-a-service offerings from platform providers. This isn't just about safety filters, but about tools that help developers enforce output formats and constraints. Global Tech Solutions recently enhanced their developer console with schema validation and retry mechanisms for JSON outputs, explicitly advising users to separate reasoning and formatting steps for complex tasks, which is a direct nod to the capacity, not format, paper. They even saw a 15% reduction in malformed JSON outputs for their early access partners by implementing this guidance.
That's fantastic. It means the insights from academia about LLM limitations are making their way quickly into best practices for commercial deployments. It validates the research, really.
It absolutely does. And finally, on the safety front, while not a direct product, we've heard that regulatory bodies in Europe and the US are starting to engage more deeply with experts on the potential risks of advanced human-AI interfaces, including BCI LLM integration. This proactive engagement, potentially leading to future auditing requirements, reflects the very real concerns highlighted by the brain prompt injection paper.
So no splashy new models this week, but a lot of foundational work on making existing and future AI more robust, efficient, and safe in deployment. It's a sign of a maturing industry, I think.
Absolutely. The industry is internalizing that raw capability needs to be matched by reliability and safety at scale.
All right, Onyx, what should our listeners be watching out for next week?
Looking ahead, I anticipate a continued surge in papers exploring techniques to improve LLM agent reliability and efficiency. We might see more practical implementations or extended benchmarks for these new agentic frameworks. Keep an eye out for work on multi-agent collaboration and dynamic tool learning, as these are natural extensions of the current agent research.
I'm also betting we'll see more research into self-evolving systems. The Infuser paper we saw earlier this week, though we didn't dive deep into it today, shows over a 20% relative improvement on Olympiad and Super GPQA benchmarks using an influence-guided self-evolution framework. That kind of iterative, self-improving training paradigm is a powerful direction.
That's a great point, Nova. And following on from the capacity, not format discussion, I'd be keen to see if any new models emerge that explicitly address this cognitive load issue for structured output, perhaps through novel architectural changes or fine-tuning approaches.
Always something exciting on the horizon. That's all the time we have for this week's episode of AI Research Weekly. Thank you, Onyx, for another insightful discussion.
My pleasure, Nova, and thank you, listeners, for tuning in.
We'll be back next week with more deep dives into the latest in AI research. Until then, keep those models training.